Yeah, thank you very much. First of all, for the invitation. It's a pleasure to be here in Kobe for these days. It's a very interesting conference. Thanks for the nice introduction, Florence. And yes, I did change my title because I realized, why should I speak about soccer in Japan? Nobody would care less about that here. So it would be much more appropriate to use baseball as an example. And actually, you will find out it doesn't matter much as long as we talk about sports. My katakana name I also put there, so you can call me Frauke. Yes, the only thing I would need is a pointer here. Yeah. Sorry. Okay, we are all set up. Yes, so I hope in the coming 40 minutes that I have, I can convince you why our subjects are really so important to us that we can consume a lot of HPC time on computers such as Riken, K-computer or post-K. So we are really from the application side. I'm aware I'm going to talk to many computational scientists here, but I hope I can convince you that these are important questions to ask and important enough to make use of many CPU hours. Where I'm from, I shortly give you an idea. You have all seen this. This is not our institute. No, you have not all seen this, but Japanese very much are intrigued to visit it. This is Heidelberg Castle up the Neckar River, and when you follow that road here, around one more corner, that is where our institute is located. It's a very nice place in a lush green neighborhood, so feel free and visit us. It's actually sponsored by a personal sponsor that is a co-founder of that software company, SAP. With not having Google or Facebook in Europe, it's still the largest software company in Europe, actually. And he is funding science on that site. Okay, so back to the topic. I will first generally introduce what we are after, and then in the second half of the talk, give you one specific topic that we are working on. So why does it hurt to play soccer, or for that matter, baseball? It's actually a Japanese baseball team here. When you look at these pictures, you directly realize there's a very high load acting on various types of tissues here. And one is the bone, one is connective tissue, such as cartilage or tendon. So generally, there's much more than just the weight of our body acting on our tissues inside. And this is very important. It's not just that we use up, finally, and this gives rise to problematic consequences, use up our tissue, but also we need this for hemostasis. So actually, if you stop moving yourself, or if you stop feeling gravity like the astronaut, you will actually lose bone tissue and cartilage and such. So there's biochemical pathways here involved, and it's by and large not clear how this all works. So how do we balance the amount of load acting on each centimeter cube in our body? And that's where we think simulations can really help, because when you look into these materials, and I didn't only put biomaterials here, but this is collagen in such as cartilage or tendon, bone tissue, other mineralized tissue, or in general polymers, synthetic polymers, what really matters for how they mechanically behave is a lot what happens on the atomistic scale. So we really need to zoom into the very last detail here. And what you see here are atomistic structures. You see these are crystals, actually carbonate crystals that appear in teeth or bone. This is a reinforced polymer here. So to go really into the atomistic scale then also requires to go back and then predict macroscopic quantities on the large scale for a mechanical function. And this not only applies to what we have in our body when doing sports, but the same applies to the balls we work with. And I only now, when I looked it up, realized the baseball is still actually made of leather. And this is nothing but processed collagen. While for footballs, one moved towards synthetic polymers a longer while ago already. And they need to be as withstanding also, right, as some of the polymers in our body. How do we in our group look at mechanical function? We more or less got motivated by what engineers do. So when engineers want to design something with very high mechanical resilience, such as in an earthquake. We yesterday visited the K-computer site, so you see how you make things sustain against earthquakes. You calculate the stresses inside the structure, up on loading it, like a car in a crash test, or a building in an earthquake, and then look at these internal stress fields in using computer simulations. And these are finite element codes. They are fairly well established. And when you see stresses building up in some of the structures, this is where you want to reinforce your structure. Now, can we do the same thing for molecules? Obviously, a molecule is not quite such a continuous thing, right? Here, steel could have been approximated by one homogeneous material, but if you zoom into these complex biomaterials, this doesn't work anymore. So what we need is instead something of that sort of method that can be applied to biomolecules, which are much more complex. And that's what we developed in the group. We call it force distribution analysis. It's based on particle-based methods, molecular dynamic simulations. I'll get to that in a second. And you see here it for collagen or for materials such as graphene applied. And again, here also where you see red, this is where stress is concentrated. Blue means low stresses. Where do we get these pictures from? As I said, our working horse is molecular dynamic simulations. I won't go into detail. I just want to mention that these are particle-based methods in which each particle, which typically is an atom, interacts with each other particle. You see already that this is computationally demanding through what is called a force field and energy function that contains all physically motivated interactions in that molecule. And actually at each molecular dynamic step, we calculate then these forces from these energies, just the derivative of the forces, to calculate how these particles move in space. And we now take exactly these pairwise forces between the atoms to get our stress fields. So this is then very simply saying, if these were now atoms with springs, these springs now can be complicated potentials, the difference in the force before pulling and after pulling on that molecule. And these forces we take and map it on the structure. Why now does this need a lot of compute power? First of all, as I said already, very broadly speaking, each atom interacts with each atom, so this is an n-square problem. Modern codes, also those run on the K-computer, use codes that scale with n log n, that do some approximations here. But also, we need very, very many time steps. And the reason is the following, and maybe this is something that you haven't thought about it too much. We live at our body temperature, right? And atoms are very light. So when you calculate the mean velocity of the atoms inside our body, you get to something in the 1,000 meters per second. So this is the jiggling and wriggling that currently, while we sit here and don't do anything, our atoms are doing, right? So this is massive. This also means, because of that high speed, we need to do very tiny time steps, right? Atoms will soon collide into each other. They vibrate around mean positions, and we can integrate our equations of motions only in tiny time steps. So in general, because of these high velocities, we need something in this order of time steps in our simulations. This is very different also to astrophysics codes. They can maybe occupy easily a full HPC center, but they then only run at 10,000 time steps, right? So they are not that optimized for these high amount of time steps that we need in biological systems. Okay, and once we have done all these time steps, we average these forces and then get these stress fields out. And I show you a bit more in detail now, a very few short examples of what we learned from this. So here you see a single graphene sheet, and it's indented from the back. And you see how then stress concentrates, and directly where stress is maximal, we start bonds to break, and we can look at really fracture. This is with an efficient molecular dynamics code. There's no quantum chemistry in here. I can tell you about details later, especially for the quantum chemists that might be interested in that. Another example is actually a piece of silk, another interesting biomaterial. It contains these very structured, what is called beta sheets in protein science. And actually, these beta sheets show hydrogen bonds that have a zigzag geometry. And when you now start pulling one of these strands out, This zigzag geometry gives rise to an alternating compression and tension in the hydrogen bonds. And this makes it actually particularly stable. In an analogy to what architects do when building houses or bridges, you also have a much better balance between compression and tension in that zigzag geometry, right? And this is exactly what we find on a molecular scale within silk. Now we look at minerals as they occur in, for example, our teeth, calcium carbonate, calcite, and aragonite crystals. They are flawed, and we here look at the atomistic level, so not with finite element calculations, right? This is not a continuum model here, but at atomistic scale, at the stress concentration at such a flaw and subsequent rupture. And we learn actually that a continuum approximation would work not so badly, surprisingly well actually for such flawed material, but of course looking at rupture is much more complicated in continuum approximations. And finally, more synthetic, and a more synthetic example is one in which we pull a polymer apart and look at strain within polymer chains, upon also reinforcing with carbon nanotubes. A few words about the code and efficiency here that we use for more the, say, computer science audience. We use GROMACS. GROMACS is a huge scientific software project. It works up to hundreds of millions of particles, even though this is not the standard, so we like to stay below 1 million to make things work. It's actually, depending a bit, I agree on the architecture of the compute cluster, but it's extremely high performance, I think one can say in general, especially because it got a really very good GPU acceleration. So it's commonly mainly used with GPUs. And got really written the very important intrinsic functions that the compiler transforms to direct SIMD machine instructions that makes it very efficient. It's also used much more, increasingly more for the material science community. And because often you talk about how much does a new HPC cluster cost, I here talk about what does that software cost. It's free, right? So it doesn't cost anything. But calculating just based on the lines it has, how many person years go into, it's actually quite a valuable endeavor that we have here and that really makes science move forward. Now, very shortly, maybe many of you are aware of that, but what is our European HPC scene? It's actually something that I think Europe is very strong is in collaborating across boundaries and the borders among Europe. So we have what is called PRACE. It's a European Partnership for HPC Computing, a network in which scientists can use compute clusters of the different countries, and those that donate compute time, which is negotiated over and over again newly, are 5 countries here with HPC centers. And actually, Germany has 3 of them, our highest level tier 0 clusters, in Jülich, nearby Munich and Stuttgart. Switzerland, France, Spain, and Italy are also in that, but all other countries that really lack dramatically compute time, say Hungary, Greece, these scientists have access to these clusters through that network. Maybe shortly looking at what has been done on the K computer, and this is maybe something that you have, maybe somebody in the audience have been involved in, which has been done in the collaboration of Sugiter and Feig and co-workers at RECON. It's among the largest molecular dynamic simulations of a biological system we have to date. They really put all what we know about a piece of a bacterial cell into the computer with all its complex ingredients. It's a soup, so to say. It's highly packed, as you see, so this is at these, what we know of, concentrations, and then you can study how really these molecules diffuse around, bind, interact with one another. So this has been an important step forward. All right. I now would move to the subject of soccer or baseball, and would remind you that mechanical load here is really dramatic. It starts hurting, so to say, when I just watch soccer. I rather wouldn't play it. And what is it in the body that takes up a lot of load? Actually, collagen is the major structure here. All have heard of collagen. It's also what you find when you go to a shop in skin cream, right? It's an old protein. We know for it for ages. And it's the major load-bearing structure of the body. It's actually the major protein of the body. It's the most common, it's the most abundant protein in our body. All the connective tissue is made from it. Everything that you see here white, not that bone here, but all that part, the achilles tendon is the thickest actually, is collagen. Now, how does collagen behave under force? It is highly elastic and resistant against mechanical load. Actually, the human achilles tendon can bear 90 megapascal, which is really several times of the body weight. So this is strong. It can break, right? One does see this. You use it up, also use up cartilage. So there's really wear in our body, which we can to some extent repair, though, which is interesting. But the question remains, what makes collagen strong? What happens when we really pull strongly on it? We had an hypothesis, which is, could it be, and this is new now, we actually also haven't published this yet, it's under revision right now, could radicals form in collagen under load? And this load as if you go jogging or play soccer or baseball. What are radicals? This is something that many of you have heard about. It's actually now high school chemistry that I just repeat here now for you. Radicals are single electrons, strictly speaking. All our biological molecules, most matter on Earth, I think one can say, does not have radicals. Single electrons rather come in pairs, right? A chemical bond is two electrons in a pair, and this is where it's satisfied. So this electron is harmless, so to say. It's not very reactive, but it becomes highly reactive once it's broken. So the analogy of a married couple is there, right? Alone you are reactive, in a couple not. Now, how would they form in collagen? So when you can imagine collagen actually has the structure of helices connected to one another. If you now pull on the protein itself, bonds will eventually cleave, and if they cleave such the electrons get separated, this is called homolysis actually, then you get radicals. Why is that so important? Why do we think that this happened? What would be the consequences biologically then? Well, interestingly, these radicals then can transform into oxidative species, which can be radicaloid or not, H2O2, for example, hydrogen peroxide. And these are signaling molecules that, for example, go into tissue damage, cancer, inflammation, and pain sensation. So if you have an inflammation, there's high levels of such reactive oxygen species here. But they are also important, it's more and more realized. They regulate gene expression, tissue hemostasis, and so forth. So if this is true, then we would have means to measure force in our body, because then measuring that force gives rise to oxidative molecules that can signal into the cell nucleus and change the subsequent biology down there. You have heard of radicals also because they are produced under UV radiation, so you rather protect yourself for this reason also from UV. And antioxidants are those you want to eat, for example, for breakfast, as an apple or green tea. So oxidative species are harmful. This is what everybody knows. I want to make the point they're not only harmful, they're harmful if you have too much of it, but biology needs them also as a signal. So at intermediate levels, this is what we need. So it's really a balance here that needs to be established. So how do we test this? First of all, with simulations, but we also now started doing our own experiments on this. And this is what I want to show you now. So how do we simulate these rupturing events? We go into the tendon. We built a large-scale structure of collagen. This is not at atomic resolution available, so this was a large integrative structural modeling effort, including, this is very important, what is called the crosslinks. So these pink balls here in the structure, this is an atomistic detailed structure, are the so-called crosslinks. They bridge triple helices, they are called, these gray lines here, next to each other, with one another. So this is where a lot of load likely will occur. We will check for this later. This is a zoom into such a crosslink. This is special for collagen. No other proteins have this chemistry here. It's actually also CN bonds. So for the quantum chemist here, we looked a lot in detail at this bond cleavage with quantum chemistry. And it turns out that what you have in the crosslink or in the protein, these CC and CN bonds cleave with the same dissociation energy in this homolytic fashion. Now, in molecular dynamic simulations, we subjected this piece, actually double the size of it, to molecular dynamic simulations, applied force outside, and then looked at where do stresses concentrate. And that's the picture we get from our force distribution analysis. What you see here again is in blue low stresses, in red high stresses. You see it's red here and there, but actually if you zoom onto these crosslinks that we have, some of them are really under maximal stresses. That they connect these triple helices moving away from one another. This is where very frequently, on average, stresses concentrate. So our prediction from these simulations, I missed to say that these are fairly huge systems. This is a 5 million atom system that we needed to simulate for many hundreds of nanoseconds. So this has been a major HPC effort, actually. We find in the crosslinks. Now, interestingly, this is now more a biological view, so to say, on collagen, is these crosslinks are embedded, these blue, they are now shown in blue, they're embedded into these clouds in collagen. So every now and then, when you walk along your tendon, so to say, these in just 30 nanometer distances, you will have these clouds. What are these clouds for the biochemists among you? These are aromatic residues, tyrosines, phenylalanines, actually also other redox active residues, methionines. They actually are known to stabilize radicals really well. So our prediction from the computer makes sense because actually it seems collagen was made to work with these radicals so that they don't propagate randomly around and make damage to our DNA. The collagen really evolved as a sink, as to catch these radicals and stabilize them at least for a while around these crosslinks. We actually looked at this a bit more detail. You see here a zoom in of such a crosslink, and you see here these aromatic residues. They actually can nicely pick up these electrons, these single electrons, unhappy on that side, but much more energetically stabilized here. And interestingly, when we look for all collagen type 1 that we know from evolution, from bird and so forth, then we find all the time these phenylalanines and tyrosines to be enriched in these sites. So what you see here are abundances, sorry, this is missing, along the collagen axis here. So many of these aromatic residues are right there. So this is, in a way, one could say, an indirect support of the computer simulation such that we really see functionally collagen might have evolved to these radicals, right? We went a bit further in these molecular dynamic simulations because the problem is we cannot really simulate bond scission here. For those that know molecular dynamic simulations, a chemical bond is truly actually a spring. This is a huge approximation, right? So you don't have electrons. They don't exist in this classical picture in molecular dynamic simulations. An atom is a ball, and two atoms are connected by a spring. That's all it is. So electronic degrees of freedoms don't exist, and they would be too expensive here. This would be really not feasible to do quantum chemistry, but we took a very pragmatic approach to simulate bond rupture, and these are the first pictures here. So you see here the collagen fiber again, and we see a spontaneous rupture actually between these two atoms marked as spheres. This is before rupture, this is after rupture, in molecular dynamics simulations on the fly. And those into methods developments or those interested in Monte Carlo simulations, what we do is, it's a hybrid Monte Carlo molecular dynamics scheme. We run MD, but every now and then we check the forces in these bonds. And if they are very high, we do a kinetic Monte Carlo step, perform bond scission, allow bond scission in this Monte Carlo step if it's not rejected, and then run MD again, and this over and over again. So the vision is to really see all that downstream chemistry on the fly in a molecular dynamics simulations. We're gonna develop this further, and this is a recipe that is even not slowing down current codes we implemented into GROMACS. Maybe one limit we have, I wanted to shortly show you. We at the moment simulate such a piece, roughly. But actually, we did a graph analysis on all these connections within Collagen, and it's clear that we have here a boundary problem. We are actually too small to say something about the macroscopic object, the tendon, say the Achilles tendon. We don't need to be as big as an Achilles tendon, obviously, but what would be the minimal size to mechanically really be predictive quantitatively? And that's what we ask with this graph analysis. I don't go into details here, but these are these D periods, how long your model is. And actually, a number 5 would be good. That's roughly what I try to draw here. This gives then at least 25 million. This is still something that's absolutely doable, and we will move towards this. So a point here is that with these material questions, you can easily pose very important scientific questions at large scale and really make a scientific point here. Okay, this was on the simulations, but then is this all fiction or not, right? That's always what we need to ask. We, in this case, decided we do the experiments ourselves. I'm a full-fledged computational scientist. I, from my undergrad studies, tried to prevent touching flasks or something like that. But in this case, it looked simple enough to do this ourselves. So we went to another lab with the right apparatus and did it ourselves. And what we needed was something that you find in each university, I think. It's nothing high-tech. These instruments sit around for 30 years already, and they also haven't evolved really because they are good enough. For most purposes, it's called an electron-paramagnetic resonance spectrometer. That's what you see here, a not so strong but not so small magnet. And in this electric field, you can look at the spin flip of your electron. So it's very sensitive towards unpaired electrons, and you don't see anything else. So it's the perfect method for our question. So what we do is we have this little tension apparatus. We put a piece, actually at the moment, of a rat tail. So we cut off the rat tail, take a piece of that tendon in the tail, and stretch it in the stretching device. We can equally do an Achilles tendon, and we will do so soon. And then put this sample into the EPR spectrometer and look for radicals. And this is here now the amount of radicals in our collagen sample as a function of the force we applied to the tendon. And you see that it grows. So we have very little radicals beforehand, and they grow with force. The signal actually looks like this. The signal itself, so this would be a little signal before stretching, and then it grows after 20 Newton. And this signal actually tells you a lot about the chemistry of the radical. And what we learned, and this was actually a long-standing miracle, what this spectrum is. We talked to many experts. It turns out that it's perfectly in line with these aromatic residues around. So the electron, before we even can measure it, hopped very quickly onto one of these aromatic residues. It's just that this one is oxidized already. That made it a bit special. It's called DOPA. You find it in some proteins. So all this oxidative stress got consumed already so that you have here hydroxyl groups. And this is a particularly stable radical species. What we then tried is to also in the EPR trap these first radicals on the crosslinks. I don't have the data here, but maybe you can believe me that when we do this at 70 Kelvin, so in liquid nitrogen, we can trap these original radicals here, and they are in line with what we find with quantum chemistry. It's actually C-C bonds that break. We see a CH2 radical at very cold temperature where we prevent that hopping. Okay, so my conclusion here is that yes, load really changes chemistry. So this load here can cleave bonds. This is new because people would have thought forces in biology are never enough to really cleave bonds. These are massive forces. Actually, one bond needs 1,000 piconewton. A protein would just unravel already at 100 piconewton, and people would have said that's the ultimate limit. We now are the first that would say, no, physiological forces are high enough to do this here. And then you have actually, according to our experiments that we did, H2O2 as a consequence. Hydrogen peroxide is the same thing you can get blonde hair from, right? It's highly oxidative, but at low regimes feeds into pain sensation, for example, so you will have higher pain in your knee when you used it a lot, is the picture, as a consequence. So radicals on a tendon that make H2O2 can make your pain sensation more susceptible to load, and thereby you use stop-over training, for example. It also feeds, as I said, into inflammation, so at some point it will have pathological effects. So conclusion would be play soccer, but only until it starts hurting. So sports is, of course, not, this doesn't say don't move at all. It says move, but don't overdo it, because too much oxidative stress is harmful. And the same applies to baseball, naturally, and all other sports. And maybe it's clear now that also running instead of in the woods or grass, running on asphalt is less, is more harmful to your body. So I would like to thank people in my group that worked on this. It's a bit of an outdated picture, but Christopher Zapp is already on this. He did the experiments and the quantum chemistry on collagen. Agnieszka Obarska-Kozinski is not on the picture. She did the molecular dynamics simulations on collagen, and Benedikt Rennekamp is the PhD student doing the reactive MD development that we are very excited to see moving also on a large cluster now soon for collagen. I thank for the funding, and I want to mention that actually what is one steady link to Japan is that we actually have for many years already funding from Toyota. It's Toyota Europe, but I find it amazing that it's, as a Japanese company, they put a lot of effort into visionary science, actually, so visionary science and technology development in their company, and that's what we, on the biomaterial side, very much profited from. Yeah, and I thank you for your attention.